good morning, good afternoon, everyone. Welcome into another exciting Exploring by the Seat of Your Pants broadcast with us here. My name is Jesse. If you're new to us, like some of our audience and our speaker are today, then we are all about bringing conservation, adventure, and science into classrooms around the world. This is our third of four broadcasts today. We've done a bunch on species at risk in Canada. We've got a cool French program happening simultaneously with this one, but I'm so excited to dive in today with a new speaker on a topic that we haven't featured in way too long, just way too long. It's very exciting to be able to bring it back to you. So a big welcome into Avoca West, Mr. Hugh Miller's class, all our YouTube groups as well. Thank you for joining us in our last few seconds before we got underway there. I want to note too, as a space broadcast, our entire space output this year has been made possible by Western Space, helping us keep it free for classrooms everywhere. So a big thank you to them for making this possible. Now I'm so excited today to welcome in early career researcher, National Geographic explorer, incredible scientist extraordinaire who's worked with some of the most storied institutes and universities in her early career possible, Dr. Munazza. She's going to talk to us today about characterizing alien worlds with the James Webb Space Telescope, which means, to wit, that she gets to use the greatest scientific tool of all time to explore alien planets. If there's a cooler job than that on planet Earth, I do not know what it is. So I'm so excited to turn you over to Dr. Alam to blow your minds and highlight some of the amazing work that she and the global scientific community get to do with the coolest of all scientific toys, the James Webb Space Telescope. I'm going to stop talking now. Welcome, Munazza. It's so nice to have you here for the first time ever. It's taken too long. I'm so thrilled to have you. And if you want to take us away, go for it.
Sounds good. All right. Well, thank you so much for having me. I'm excited to be here and tell you a little bit about the work that I do as an astronomer using observations from the James Webb Space Telescope, or JWST for short, in order to study the atmospheres of exoplanets, or planets beyond the solar system. So this picture is a picture of the telescope, JWST, when it was launched from French Guiana on Christmas Day in 2021. This picture is our last view of JWST before it started on a month-long journey to its final destination 1 million miles away from our planet. And the launch of this telescope is incredible. It represents one of the greatest scientific and technological accomplishments in human history. This telescope is going to collect light from distant planets and the oldest galaxies, and it's going to give us a snapshot into what the cosmos looked like billions of years ago, and will unveil to us the universe like never before. The promise of JWST was clear from the first images of the universe that it took. This is the first JWST deep field image, and it was unveiled by President Joe Biden in July 2022. This image is incredible because it represents a portion of the sky that is approximately the size of a single grain of sand held at arm's length. That is how clearly we can now see the universe. From Galileo's first telescopes over 400 years ago, to the first large ground-based telescopes that were built in the late 1700s, we have been building bigger and better telescopes over the past few hundred years. And the launch of the Hubble Space Telescope in 1990 marked a massive milestone in telescope history. It was not only one of the first space-based telescopes, but it was also the largest and the most flexible, with capabilities to observe precisely at a wide range of wavelengths or colors of light. With Hubble, we're able to observe the atmospheres of exoplanets to extreme precision, so very carefully. And for the first time, we were able to characterize the weather on these other worlds. From these Hubble observations, we discovered alien worlds within our very own Milky Way galaxy, such as planets with raindrops made of corundum, the mineral that makes up rubies and sapphires, as well as worlds so dark they appear charcoal black. And from this groundbreaking view into exoplanet atmospheres with Hubble, we are now expanding what's possible to observe with the recently launched JWST. JWST is about the size of a tennis court, and it's the largest and most powerful space telescope ever built. Hubble was roughly the size of a school bus, but JWST is much larger. And so I said that it's the size of a tennis court. And if you want to look at the telescope in comparison, just look how small the people look next to JWST. This golden beehive structure is called the primary mirror of JWST, and it's about 6.5 meters in diameter. It's about 3 times the size of Hubble's primary mirror. And a telescope's primary mirror is important because it determines the amount of light that a telescope can collect, which increases the power and the capability of the telescope. All right, let's take a tour of JWST's main components. So in orbit around the sun, 1 million miles away from Earth, one side of JWST always faces the sun, and the other faces planets, stars, and galaxies that we wish to observe. So on the observing side, we have the primary mirror and the secondary mirror, which collect and focus light from distant sources, as well as the instruments that split up the light from these distant sources and help us understand what that light is made of. We also have a sun shield with 5 layers that protect the telescope from getting too hot. JWST's instruments actually need to be kept at extremely cold temperatures, below minus 370 degrees Fahrenheit, in order to work properly. And on the sun-facing side of the telescope, we have star trackers, steering and control, as well as an antenna for communications with Earth. But what exactly are the aspects of JWST's design that allow us to peer so deeply into the universe? Well, first off, JWST sees light from the universe at infrared wavelengths, which are longer than the human eye can see. At these colors, we're allowed to capture a glimpse of the light emitted from the early universe billions of years ago, because the farther that you look into space, the more redshifted or stretched out that light becomes. Fainter stars and planets that are also brighter in the infrared, and so we are able to observe dimmer targets. From the first images and data that has already come down from JWST, it's clear that JWST is performing better than expected and providing us with excellent and high quality data. And that's because with JWST, we have 10 times better spectral resolution of the data that we obtain. Spectral resolution essentially means that the data that we obtain is going to be 10 times crisper than previous Hubble observations. To give you a sense of what that means, here's a side-by-side comparison of an image taken with Hubble on the left and JWST on the right of a portion of the sky called the Pillars of Creation, which is a structure in the Eagle Nebula that's made of gas and dust. And just look at how much more detail we can see with JWST's capability to look at higher resolution and at more stretched out infrared wavelengths. In fact, with JWST, we have a wider wavelength range that we can observe with that is approximately 10 times wider than that of Hubble. Whereas with the Hubble Space Telescope, the instruments could observe about 2,000 nanometers in wavelength. With JWST, the instruments cover about 20,000 nanometers in wavelength. And the data that we get is also going to be 10 times more precise than Hubble data, with smaller error bars that will really allow us to better understand exactly what we are observing. So, how are we using JWST to take the most detailed look to date into exoplanet atmospheres? Well, the technique that I use to measure exoplanet atmospheres relies on observing planets when they transit or pass in front of their host stars from our vantage point here on Earth. And I've got a little cartoon here illustrating this technique. So the yellow circle is the star, the black disk is the planet, and then the surrounding blue ring is the atmosphere of the planet. And we see that when the planet is in front of the star during transit, the planet is going to block out a fraction of the star's light that is proportional to the size of the planet. And that dip in the brightness of the star is shown here on the bottom, and it's called the transit light curve of the planet. This is an example of a real transit light curve that was taken by JWST, where the yellow points mark the dip in the brightness of the star due to the planet's transit. And we can use transit observations like these to go one step further and characterize a planet's atmosphere, because if we observe transits at different wavelengths or colors of light, we find that the size of the planet varies. This technique for characterizing atmospheres is called transmission spectroscopy. And I've got a little cartoon here showing this effect for a planet in transit. So on the top, again, we've got the planet shown in the black disk, the planet's atmosphere shown by the surrounding colored ring, where this time the different colors represent observing at different wavelengths of light, and the star is the yellow circle. And depending on what wavelength we're looking at, that planet can appear bigger or smaller. And that's because at wavelengths the planet appears larger, that's where its atmosphere is more opaque, because that's where absorption by atoms and molecules that are present in the planet's atmosphere will occur. So here's an example of this effect using real JWST data. So in the top panel, we're looking at the transit light curve for a planet, but this time we're observing at 3 different wavelengths or colors of light. And these are represented by the green, the blue, and the red points. And if we zoom in on the bottom panel, we can see that the amount of starlight that's blocked by the planet varies very slightly at these wavelengths. And the reason for this difference is that the planet's atmosphere blocks less light at the wavelengths represented by the red points, but the planet's atmosphere blocks more light at the wavelengths represented by the green points. And for this particular planet, the green points have a deeper transit, and the planet will block more light at those wavelengths because there is absorption by carbon dioxide in the planet's atmosphere. So we can make a measurement of how much starlight the planet's atmosphere blocks at different wavelengths in order to figure out what the planet's atmosphere is made of. This measurement is called a planet's transmission spectrum, and I'm showing a cartoon spectrum here. So all of the little bumps and wiggles that you see in the transmission spectrum are fingerprints of the absorption of different atoms and molecules in the planet's atmosphere. Now, the size of this effect, how big these bumps and wiggles are, depends on the size of the planet relative to the star, as well as how puffy the planet's atmosphere is. And the signals that we're looking for are tiny. In the best case scenario for a big planet, a giant planet with a puffy atmosphere, we're looking for changes in the amount of starlight blocked that are about 0.1%. So very tiny. And if we want to push down to smaller planets that are similar, for example, in size to Earth, that means that we're pushing down to signals that are about 0.25% in size, so even tinier. And while this is a challenging measurement to make, it has been a very successful method for measuring the atmospheres of giant planets. This is the transmission spectrum from JWST of an exoplanet called WASP-39b, which is a hot Jupiter. A hot Jupiter is a planet that's similar in composition to our own solar system's Jupiter. It's a gas giant, but it's so close into its host star that a year on this planet is just 4 days long, which means that it's very hot. And from these JWST observations, we see a bump around 4.2 microns at this wavelength range. And this bump is because there is carbon dioxide in the atmosphere of this planet. And these data were actually one of the first in-depth observations of an exoplanet atmosphere that were taken with JWST. But while JWST is great for observing these bright planets and these large planets like WASP-39b, it really focused in at first on one of the best planets that was the best to observe. But if we want to search for life, WASP-39 is not one of the best planets. For that, we need to start pushing down to Earth-sized planets and rocky planets. And now with JWST, we finally can start pushing down to these smaller planet sizes in order to get excellent and high-quality observations for these smaller planets. The first of these planets that was observed with JWST is called LHS 475b. Let's take a look at what the JWST observations look like. So this is the transit light curve as observed by JWST. And again, the purple points here show the starlight that is blocked by the planet in transit. And if we measure the amount of light that is blocked by the planet's atmosphere at different wavelengths, we find that the transmission spectrum of LHS 475b looks like this. So the white points here are the JWST observations, and the colored lines show ways to interpret what that data might be telling us about its atmosphere. From these observations, the first thing that really jumps out is that we don't see any large bumps or wiggles due to absorption by a specific molecule like we did for WASP-39. And that's because for smaller planets, their atmospheres, if they have them, are much smaller and much thinner. They're not that puffy. And so the changes in the amount of light that the planet's atmosphere blocks are extremely tiny. And with these observations, we can't exactly tell the difference between these lines, but we now have a telescope that has the power and the precision that can even tell us this. And that is huge. Because for the first time ever, we have a telescope that we can use to carefully explore the atmospheres of smaller planets. And it's exactly the techniques like transmission spectroscopy that we're going to use in order to characterize the atmospheres of smaller planets and habitable worlds in the first step for searching for life beyond Earth. So we're not there yet, but the adventure is just beginning, and it's been so exciting so far that I can't wait to see where it takes us next. Thank you.
Thank you. What a cool story that is. And we've got so many classes to dive with, a whole bevy of questions and all of this and more. You featured some of my very favorite things. Before we got underway with the broadcast, one of your first pictures was this deep field where, again, it's the amount of sky that is equivalent to a grain of sand held at arm's distance. And that's how many galaxies that we can see. Not stars, not planets, but like whole hundreds of millions, billions of stars in one little grain of sand. And that would be true for every other patch of dark sky. Like, it's almost unfathomable how many potential planets there are to discover out in the universe beyond. And it's what makes your job so exciting. So thank you for sharing all that, Munazza. As I said, we're going to dive in with questions. YouTubers, please feel free to share as many as you can over the next few minutes. We'd love to come to you all. But we're going to start with Avoca West, our grade 3s in Glenview, Illinois. If you guys want to kick us off with your first question in your lunch hour, come on in and take us away.
If after Lily's first.
Hey,
You
guys.
two are already, if you have questions.
Hi.
Okay, Lily, come on up.
Hey, Lily.
So my question was, when and why did you get interested in studying this?
Ooh.
Yeah, so I got interested a bit later in life when I was in college and studying this. And the reason for that is because I grew up in New York City, so I never had a backyard telescope. I never really had any dark skies to look up to because the city lights will outshine the stars. But I was always a very curious kid, and I was always interested in understanding how the world worked. And I used to ask my parents why and how all the time. I think my questions were very annoying to them. And it wasn't until I started studying physics in high school that I really started to get the answers to those questions of why and how. And so I knew when I went to college that I wanted to study physics. But when I went to college, I met a professor who was an astronomer. And she invited me to join her research group and travel to observatories to take data. And that was when I first decided that I loved astronomy and that I wanted to continue it long term.
A beautiful answer. I grew up in Toronto, so like you, there's like 10 stars in the sky at night. It's not exactly this incredible starscape, but a lot of our classes today are in really urban areas. And if you are in a place like that, talk to your local university, go to a library. Two other recommendations, like if Star Walk 2 is an amazing app just to explore the night sky, sort of identify the things that you might be able to find, planets, stars, etc. So it's a really cool free app. And also, if you get the chance to look at the moon through a telescope, even good binoculars, it's right there. We all see it every day. It seems so trite, but like looking at the moon up close and personal is a really transformative, profound experience. So no matter where you're joining from, those little observations go a long way to putting you on a career like one we've got the chance to hear about today. Mr. Humiller's class, grade 7-8 in Waterloo, quickly becoming a very big engineering and space hub in the world. If you guys want to come in for a question, we'll come to you. Our Kruger class, Cerritos, we're coming to you next if you want to flick on your mic. But welcome in Waterloo, guys. Hey. Hey.
We've got William. William's got a question. Future astronaut in the making.
Yes.
how do you calculate movement of planets? How can you tell how quickly a planet is moving?
Yeah, so there's a couple of different ways that you can calculate the movement. So one of the ways that you can do it is modeling the movement based on the radial velocity or the Doppler wobble. So you can get how the size of the planet and the mass of the planet, and you can also when you observe transits, see how often the planet passes in front of the star. So then you get some you get a constraint on what the orbit is of the planet, and from there you can get information about its size, its mass, its gravity, and then you can and if the orbit is in a circle or more of an oval shape, and from there then you can use some equations in order to calculate the velocity of the planet.
It's really quite amazing that we can do this with things that are so far off. My favorite analogy for the power of some of these telescopes is that if someone were to light a match on the moon, you can see that very easily with something like the James Webb Space Telescope. Like, it's insane how sensitive these instruments are to be able to identify something like that. How many light years can we look back? Like, how far or distant can we look with this? Is there a figure on that?
The farthest reaches of the universe with JWST.
Pretty cool. Well, we are going to head to our Cerritos, California group, Miss Kruger's class and Miss Padamali's class. Hi, guys. Welcome in.
Go ahead.
Hello.
Go ahead. Ask your question, sweetie.
My question is, what is the closest exoplanet to Earth?
Ooh.
So the closest exoplanet to Earth actually orbits the closest star to Earth, which is called Proxima Centauri b. And that planet is a rocky planet. So it's about 4 light years away. So if we wanted to travel to that planet, it would take us 4 years to get there if we were traveling really fast at the speed of light.
And I want to harp on this for a second because we have nowhere near the capacity of traveling that fast. And so there's a figure offhand. You might actually know this. How long would it take to get there with the fastest spacecraft we've ever had? Do you know this offhand?
Oh, I'm not sure. It would be within our lifetimes, but much longer than 4 years for sure.
It's an incredible, insane amount of time. And our fastest spacecraft can like do the entire Earth like in a circle in like a second. So it's going to be a long time before we're likely to be able to get to something like Proxima Centauri b, but that's why we have telescopes and we have these tools to identify them from far away. So very cool question, guys. We've got a question online. I love this question. I knew you were going to get it. Do you think there is alien life in the universe? I love when we get this for astronomers, astronauts alike. What is your take?
Yeah, I think we know of thousands of planets that we have discovered, and we're characterizing, tens of them now and learning about their atmospheres. I think statistically speaking, I don't think, considering the number of planets that we have out there, that Earth is the only planet with life. Maybe it's not intelligent life like us, but I do think that there is life out there, and it's one of the reasons that motivates me to continue looking at small planets and studying their atmospheres.
It would be the greatest discovery in the history of science if we were ever to find alien life, whether a signal from an intelligent species from really far away or something like microbes, even on Europa, Mars, etc. But universally, I will say for our kids, every single time we have an astronomer, astronaut on, they say this. I mean, if you look at that James Webb Ultra Deep Field picture, like there are more planets out there than there are grains of sand in all the beaches of the world. And to think that Earth, which basically the moment the Earth cooled, life formed in it. Like the moment it had the capacity to form life, it did. The thought that in all the vastness of the universe, we wouldn't have that seems like an awful waste of space. So I'm really glad you answered that. And that's a great question, guys. All right, Illinois, we're back with you. Come on in on your lunch hour. Grade 3s, take us away. Hi.
Elliot, come on up.
How many planets have you seen?
Ooh.
So in terms of how many we've discovered, so we've discovered over 5,000 planets, but we have a new space telescope that's going to be launching soon called the Roman Space Telescope, and that is predicted to find over 100,000 exoplanets. So we are very quickly going to be vastly expanding the number of planets that we know of.
Follow-up question. Why will the new one be, like, what is the reason that the new one will be able to find so many more? Is it because of its specificity in finding those things like the transits, or what's the deal?
So one of the reasons why we'll be able to find just so many more planets with Roman is because it's going to have a really wide field of view. So if we think about what part of the sky Hubble could see, it was a small part of the sky, but Roman will observe a much, much bigger part of the sky all at once. And it'll have really incredible, precise instruments on it that are going to be able to see a much larger part of the sky, and then therefore find many, many more planets while it is up there in space.
How cool is that? Thank you so much. All right, Mr. Hughes class, 7/8, come on back in. Maybe we've got some more astronauts to be in that class. It's going to be an astronaut-heavy class, I think, in the future in Waterloo. Come on in, guys. Hey.
Oh, sorry. I think we're unmuted now. All right,
Yes,
Lauren.
you are.
Lauren, go ahead.
What's your favorite part about studying that?
Favorite part about studying all this?
My favorite part about studying all this?
Yeah.
I think for me, one of the most incredible parts about doing this is realizing that we are able to learn a great deal of information about the atmospheres of planets that are so far away that we can't directly see. These planets are super far away and they orbit stars that are much, much brighter than them. And yet we can indirectly, by measuring transits, learn about if they have clouds in their atmospheres, what those clouds are made of, and exactly how cloudy they are. And that is such a wonderfully profound thing that I think about every time I work on a new observation.
You are you wax so mystical about all this, and it's so nice to see someone so passionate about space exploration. Is there any resource or book or video series, whatever, that you'd also recommend for our students to get them as excited as you are about all this? Because you've done an amazing job today, but I know that one 40-minute broadcast isn't enough to really drive home the excitement of space. So any plugs?
Yeah, there was actually a book that I helped work on called Absolute Expert Space, which goes through a variety of topics related to astronomy. And I have some more information about my story and how I got into the work that I do in that book. So I definitely recommend checking it out.
Amazing. I'm going to get up the link to that for all our YouTube classes. So stay tuned for an email after this. If you're registered for today, we'd love to get you that info and keep the excitement going. And in the meantime, we're going to head back to California. If you guys have another question for us, come on in and take us away, guys. Hey.
Go ahead. Go ahead. You're right in front of.
Yeah.
Just ask your questions.
What is the most lifelike exoplanet you've discovered, and how many light years away is it?
So we have some planets that we think, so we haven't discovered anything that is like possibly a candidate for life yet, but the best types of planets that could potentially have life on them would be rocky planets, so very similar to Earth, as opposed to gas giant planets like Jupiter. And also those are planets that are going to be a bit cooler, so that they could have liquid water on their surface. We think that's really important for life. And so these types of planets are the ones that we should focus on when looking for life. And they're all within our galaxy, but depending on exactly which system they're in, they can be a variety of distances away from us.
I'm going to follow up on this with things that are a little bit closer than some exoplanets. Can you speak to some of the places in our own solar system that might have some liquid water? I know it's not your main area of expertise, but something that we might get to in the next few years, perhaps, with some cool NASA missions on the go. Where could we find life possibly in our own solar system?
Yeah, I mean, there's a lot of kind of ideas about life within our own solar system. A lot of the moons, for example, on Jupiter and Saturn, we think may be potential places where there is or was life. But yeah, it's a matter of sending out probes and going to check them out and see what's there.
It's such an exciting time in the history of space exploration, because whether you're interested in being an astronaut and going back to the moon, or setting a gateway around the moon, we've got all these incredible missions both on Mars and throughout our solar system, and now we've got the James Webb Space Telescope and even more launches in the years to come. So truly, like, if you're keen on space, if you want to be an engineer, an astronomer, like, there's more options for you to get involved in this career than there's been probably in human history. So I think it's a very exciting time for our students from grade 3 through grade 7 today. You guys are just the right age to make this possible. And I have, by the way, to inspire you further, just linked in the Absolute Expert Space link on our StreamYard and YouTube chat. So do check that out when you're done. Lots of fun opportunity to keep the learning going. Time flies when you're having fun. We are nearing the end of the broadcast. So, Munazza, is there any last message you want to leave us with about space exploration, discovery, your work, something to wrap up with today?
I guess I would just say that no matter what your interests are, whether it's space or something else more close to home, just keep looking up, keep looking forward, and always remember to be nice to everyone around you.
What a beautiful message. No one has ever said something like that to finish up. Thank you so much for that. And what we do to wrap up every broadcast, I'm going to bring in all our teacher friends to say a big thank you and farewell. So California, Ontario, Illinois, people on YouTube, thank you all so much. Have a wonderful day, everybody. Bye for now, guys.